Hello, this is the first of my series of videos in vector calculus. I always like to start with a summary sheet at the front, and these are the main ideas for the video. I like to do this because one, it makes me feel like the task at hand is manageable because I can fit it all on one sheet, but you'd be surprised how much I can fit on one sheet. But two, I also like it because it's a good way later for reviewing. I have all the key points here. I will go through several examples, and by way of review, I will have one or two problems for you to try. As a teacher, I feel obligated to tell you that, like many math courses, vector calculus starts off with some very basic ideas, and then there's things that are a little bit harder, but I urge you to try to understand how the parametric equations work, because these actually are going to be the basic things in vector calc. Later on, by the end of the semester, this stuff is going to be the easy stuff that you should really have under your belt. So get these basics, this first chapter, get the basics down. So it'll be there for you at the end of the course. It really does get much more difficult than this. It's manageable, but this is just the beginning. We are going to start by talking about vectors in R3, that is, vectors in three-dimensional space. You are hopefully familiar with R2, where we represent points in two-dimensional space by two coordinates. An x-coordinate, which tells us how far we go on the x-coordinate, in this case 2 units, and then the y-coordinate tells us how far we go up on the y-axis, in this case 3 units, and then we look at their intersection for the y equals 3 and the x equals 2, and then that will become our point 2, 3. And then in physics and also vector calculus, we will say that this point 2, 3 is the endpoint of a vector that goes from the origin to the point 2, 3. And this vector has both magnitude and direction. And this vector has both a length, which we can calculate using Pythagorean theorem, and a direction, which is 2 units to the right and 3 units up will be its direction. Another thing you should know about this vector, I had used the origin to orient my vector, in other words, to determine the direction of my vector, but once I have the direction, I can actually move my vector anywhere. And this vector here, because it has the same magnitude and direction as my original vector, these two vectors are considered equal. Now we're ready to come back to R3. So vectors start at the origin, and then they have magnitude and direction. Once we have their direction, as you saw here in R2, we are free to move them around. The way we graph them, generally the x direction is considered coming out at you, but we kind of draw it a little bit at an angle. The y direction is out to the right, and the z direction is pointing up. If we want to graph the point 2, 4, 4, we have to come out 2 units in the x direction, 4 units in the y direction. And when we graph, so our 2 units, we kind of draw our line parallel to 2. And for y to be parallel to 4, we have to draw this line parallel to the x-axis. And then from here, we go up 4 units. And that will be our resulting vector. We will come back to these statements after we've talked about vector addition and multiplication. Our next topic is vector addition. So if we have two vectors in 3 space that we want to add together, the first vector with coordinates x1, y1, z1, and the second with coordinates x2, y2, z2, and we add them together, what we do is we add them component by component. So we add x1 plus x2, that will become our new x-coordinate. y1 plus y2 is our next second coordinate, and then z1 plus z2 will become our new z-coordinate. It's important that you are able to see the geometric interpretation of this as well. So if we have a vector 3, 1, and we want to add it to the vector 2, 4, we can add the two x-coordinates, 2 plus 3 to get 5, and then the 4 plus 1 also to get 5. So our resulting vector is 5, 5, and if I drew this nicely to scale, it would match up perfectly. But the way to see this geometrically is I can think of moving one of my vectors so that the tail of the vector is at the head of the other vector, and then the resulting vector here or this resulting endpoint, will be the addition, the sum of my two starting vectors. This is often referred to as the parallelogram law, because if you consider your original two vectors as the sides of a parallelogram, and you complete the parallelogram, making the top parallel to this vector and the side parallel to your other original vector, then take the diagonal. The diagonal will be your resulting vector after you add the two original vectors together. It's really important you get not only the algebraic definition, but also the geometric, which brings us to subtraction. If we wanted to subtract b minus a, the first thing we would do is, and actually I haven't talked about this yet, so I should have talked about scalar multiplication first. But anyway, when you have a negative, it's the same vector as a, except in the opposite direction. So in other words, it's along the same line, but it's the same length as a in the other direction. So here's our minus a. And now we can consider b minus a as the sum of b with negative a. So this point over here at the end of my parallelogram is b minus a. And something I will show you right now, this point here, the b minus a, if I take this vector and I move it over, it's the same vector that goes to the points b and a. Keep that in the back of your mind because that is something that you will see several times later. Next, we come to vector multiplication. First, we do scalar multiplication. That is, we multiply our vector by a scalar a. And scalar meaning it's just a real number like 2 or 3 or pi. It's not another vector. And to do our scalar multiplication algebraically, we just multiply each component x, y, and z by a. Algebraically, the scalar multiplication does not change the direction of your vector. It stays in the same direction as the original x, y, z vector. What a does is it scales by a factor of a, which is probably why they call it scalar. It's something that scales your vectors. Geometrically, if we have a vector a and it points in the x direction, in the positive x direction, so this vector is the vector 2, 0. If we scale it by 2 or multiply a by 2, we still have a vector pointing in the positive x direction, but it has been, its length has been made twice as long. So now we're at 4, 0. If instead we scale our vector by a factor of 1/2, now our vector is going to be half as long as our original vector, still pointing in the same direction. Now that we've talked about how to multiply a scalar times a vector, we need to consider how do we multiply a vector by a vector. And there are two ways we can do that. The first way is called a dot product, and it takes a vector, you multiply it by another vector, and it produces a scalar. The second way is to do a cross product. It takes a vector, you multiply by another vector, and it produces another vector, a third vector. So these two things, they're not complicated, but they do deserve videos on their own. So we will not talk about them any further, except to say there are two: the dot product, the cross product. The product of the dot product is a scalar. The product of the cross product is a vector. Now we are ready to go back to these notational things over here, now that we know how to add vectors and also multiply vectors. So the idea here is that you can write vectors in terms of a standard basis. And by standard basis, we mean we want a set of vectors that represent the directions, our main directions in our space. So for R3, our main directions are the x direction, the y direction, and the z direction. If we were in 2 space here, our main directions would be the x direction and the y direction. And we want to represent those directions as simply as possible. So to represent the positive x direction, we can represent in 3 space that by E1 or I, they both have the same value, and the value is 1, 0, 0. So here's I. And this I should be written like this with a little hat on top, but I couldn't do that on my computer, so I also hand wrote it. So our first basis vector represents the x direction and is 1, 0, 0. And again, we did this the simplest way possible, so we didn't put like 15, 0, 0. We wanted something that had length of 1. Our next basis vector represents the y direction, so that's 0, 1, 0. And we also sometimes call that the J vector, and with a little hat, J hat. E3 represents our Z direction, also represented by a K hat, and that's 0, 0, 1. So any vector x, y, z, we can write that as the x coordinate times the E1 vector, or the I vector, the y coordinate times the E2, or the J vector, and the z coordinate times the E3, or the K vector. You will see this notation everywhere in books. This one's not quite as common, but I just want to make sure you had seen it in case it comes up. That is not to say the E1, E2, and E3 notation is not common. If you've taken linear algebra or you do take linear algebra, the E1, E1, E2, E3 is all over the place. The last topic on our overview slides is parametric equations, and I did summarize each of them by putting the equation associated with each, but they really need more thorough treatment, which we need to devote more space to. The first parametric equation we are going to do is parametric equations of a plane whose adjacent sides are the vectors A and B. And I have drawn this in R2 because it's much easier to see and work in R2 than R3. But essentially you are going to be using this in R3. In R2, the plane defined by two vectors is actually just the xy plane, so it's not interesting. In R3 it becomes more interesting. But again, we're using R2 because it's easier to visualize. I'm going to go through this example with a lot of detail and a lot of steps. One, so that you get a really good idea of what's going on, and two, so that our other two parameterizations, if we have a good foundation or understanding of this one, the other two will go very quickly. I have my vectors A and B here drawn out, and I will use these vectors to define the plane that these two vectors lie in. I want to start by adding my two vectors using this vector addition. I had said that we could move our vectors here, and that will define this parallelogram. And this point here that I have in blue, we get by adding our two vectors. Next, I want to ask, what would happen if I multiply my vector A by 1/2 before I add it to B? From our discussion about scalar multiples, what that would do to A is make it only half as long. Now when I move this vector A, or 1/2 A, so I can use the parallelogram law, and I'm going to complete my parallelogram here, I get this point in blue. I'm going to do that same thing again, except now I'm going to scale A by something even smaller, 1/4 of A. And again, I'm going to use my parallelogram law over here, and I see that the resulting point is this blue point here. And just to be that way, next I'm going to try to scale A by 3/4. Again, moving my vectors around, this is my 3/4 A that I'm moving to the top, and this is my vector B that I move over to meet my 1/4 of A, and this is the resulting point. We can continue in this way, and what we will see is that if we multiply our vector A by a scalar s and then add it to 1 times b, and we let s vary between 0 and 1, the line we are going to get is this blue line here. We can do something similar with b, so we can add 1/2 b to A. Here is my 1/2 b vector, and I'm going to move it over here to the end of A, and then I'm also going to move my A vector just so it points to the tip so we can see where this resulting, if we used our parallelogram law, the resulting vector would be. I do this for another point, a 1A added to 1/4 B, so here's my 1/4 B, and I'm going to move it so I can use my parallelogram law. I'm going to move my A so it meets my B, and I get this point here. So let's jump ahead a little bit, and we'll say that if we add a multiple of B, so TB, where T goes between 0 and 1, to A, we are going to get this line here. All the points of this nature give us this line. All the values of S will give us this line. Now let's see what will happen if I take a equals 1/2 and b equals 1/2 and add them together. I am going to move my 1/2 of a and my 1/2 of b, so the point I get is this blue one here. And now, just so you don't think I have to have the same, and this is the reason why I chose T for B and S for A, I'm going to have different scalars in front of A and B, and I'll add them together. So I'll have 2/3 of A and 3/4 of B, and I'll get this dot over here. If you keep choosing different fractions to scale A and B by, what you'll see is that AS plus BT for values of S and T varying between 0 and 1, and S and T, the reason why they are separated out, the reason why it's not AS plus BS is because you want S and T to be able to have different values like this one here. But the values between 0 and 1 will give you all the points in this parallelogram, including the edges, when S and T is equal to 1, when S and T are equal to 1. So this is the parameterization of this parallelogram, including the interior. And that is this formula here. But we wanted the equation of the plane, so we need the stuff outside over here as well. To get those points, I'm going to look at what happens when I start scaling things by negative values. So I'm going to start with -1/2 a plus b. So here I have a vector in the same direction along the same line as a, but in the negative direction and half as long. And if you wanted to get the coordinates, the exact coordinates, you would do the -1/2 for 1, which is -2 minus 1/2. Again, now I'm going to do my A, my -1/2 A, my B, and I get this point at the edge, which actually I can't reach because the software I'm doing won't let me do that. But here it is. It's outside. This is as close as I can get. And the other variation I'm going to do is multiply A by something larger than 1. So here I have 2A. Here I have my 2A vector. Here I have my B vector, and I am going to get this point out here. So what we get, as we have AS plus BT and we let S go from -infinity to infinity and T goes between 0 and 1, we get this entire line here. And now when we do the same thing for B, in other words, we let T go from -infinity to infinity, and S just goes from 0 to 1, we are going to get this line here, the infinite line. In the same way, when we looked at vector A and vector B and we added up all the points in between, we got the entire parallelogram. Now we have an infinite vector A and an infinite vector B, and when we add up all the points, we're going to get all the points in the plane. Now we've done parametric equation of a plane whose adjacent sides are vectors A and B, and we're ready to do line passing through the endpoints of a vector A in the direction of V. This one should go a little faster. We're looking for the parametric equation of a line passing through the endpoint of a vector A, which I have a vector A, 2, 1 here, in the direction of a vector V. So I have the vector V, 1, 3 here. We're looking for the line that goes to this point A and is in this direction V. And we're extending this vector so it goes out and becomes a line. We've kind of gotten used to adding vectors, so I'm not going to do all the moving vectors around. But if I add A plus V, I get this point here, which is nice because it's on the line that we're looking for. And if you recall from our last example, if we have A plus TV, where T goes between 0 and 1, we get this entire line here. And you will also recall, as I start adding negative values for T, I start getting points on this side of A. And as I start multiplying V by values greater than 1, I'm extending my V, and I'm going to start getting points out here. So our line is just going to be A plus TV, where T goes between -infinity and infinity. And this equation here, we often call it L of T because that's an equation of a line parameterized by T. And this is something worth remembering, that to get an equation of a line, a parametric equation of a line, you need a point on the line, and you need a direction vector. So if on an exam you're asked to give a parametric equation of a line, it's always good to go back and say, well, what do I need? I need a point on the line, I need to find a point on the line, and then I need to find the direction. Our last parameterization is the equation of a line passing through the endpoints of A and B. So this blue line is the equation we are looking for. And you also want to remember when we talked about parameterizing a line, I said we needed two things. We needed a point on the line and the direction of the line. So we can take A or B as a point on the line. In this case, just for whatever, because we have to choose one, I'm going to choose A as my point on the line. But now I need the direction for this line between A and B. And we're going to go back to this two-dimensional case here when we were just talking about subtracting A from B. If you recall, for B minus A, we would take A in the opposite direction. Remember, the scalar is just you multiply A by -1 and you get this negative A here. I completed my parallelogram with B, so B and minus A here. And this is my point of B minus A. And what I had mentioned, just to kind of keep in mind, is this B minus A vector is in the direction of the line between B and A. And remember, we can move vectors around. We don't have to keep them at the origin. So this is our direction vector, B minus A. We will apply that to our example here. So I start by marking out minus A. And now to get my parallelogram, I can move A perpendicular, slide B over, and I get my resulting vector B minus A right here, the diagonal of the parallelogram. Now I'm going to slide this vector B minus A without rotating it. I'm going to do my best to keep the same orientation, same direction. And what you can see is B minus A is exactly the direction vector of the line between A and B. And here is your parameterization. Again, there's a lot in this example that you're going to be using in the future, so it's good to get to know this. Hence, B minus A is our direction vector, and we can plug it in. So the equation of a line, again, to get a parameterized equation of a line, you need a point on the line, which we chose A, and a direction, which is B minus A. Also note, B minus A, when you do B minus A, it is the vector that goes from A to B. So think of B minus A as being B is the ending point, and you subtract off A. So you start at A, you end at B. That is the vector B minus A. Just to remind you exactly why the direction goes, the point goes from A to B, is when we did this subtraction of B and we added it to minus A, we drew our parallelogram, and then we went from the origin to the point. So this is the direction from A to B. That is the direction of our vector, and then we moved our vector up. And I just want to mention, when I say you don't want to memorize these formulas, I'm not saying that you want to draw 1,000 little parallelograms and the dots on it to figure out the parameterization of anything. But what I am saying is you should understand how this came about and have it somewhere in the back of your mind in case you need to parameterize something, some variation of this. And then for a line, you definitely want to remember, for a line, you need a point and a direction. So just remember, the two things you need are a point and a direction. You multiply your direction by your parameter t. Once you can remember that, then the parametric equation of a line passing through endpoints vectors A and B should come easily to you because you're very familiar what B minus A looks like, and that you can translate it over and it'll give you the direction. So it's those understandings that I'm telling you you want to be have in your head. For review, here are some problems for you to try. As I had mentioned, all the examples I had given you were in R2 because it was easier to draw and visualize. But these are examples or problems in R3, but the techniques are the same, and of course the formulas are the same. These are the solutions. I hope you found this useful, and thank you for watching.